You know, when we look at a matrix, it's easy to just see a grid of numbers, right? But what if I told you they have a secret life? That inside they have these hidden structures, these surprising properties, almost like a personality. Today, we're going to pull back the curtain and uncover that secret life together.
All right, so here's our game plan. We're going to look at the two faces of every matrix, then we'll uncover a really cool decomposition secret. After that, we'll get into the matrix undo button, what it is and how to find it. And finally, we'll connect it all back to why this stuff actually matters in the real world.
Okay, first up, let's talk about the two fundamental personalities that every single square matrix has hiding inside it. You can think of them as two sides of the very same coin.
And this slide just lays it out so perfectly. On one side, you've got the symmetric matrix. That's where if you flip it along its diagonal, what we call the transpose, it stays exactly the same. On the other side, you have its moody twin, the skew symmetric. You flip that one, and it becomes the negative of what it was before. See? Two sides, totally connected. So, what does it actually mean to be symmetric? Well, just imagine putting a mirror down on that main diagonal, the one that runs from the top left to the bottom right. If every number on one side of the mirror is a perfect reflection of the number on the other side, bam, you've got yourself a symmetric matrix. It's all about that perfect balance. And now for the alter ego, the skew symmetric matrix. This one's a bit different. When you flip it, every element becomes its negative. But here's the super interesting detail, the dead giveaway. For that to be possible, every single number on the main diagonal has to be 0. It's the only way the math works out. It's a non-negotiable rule for these guys.
So you might be thinking, okay, symmetric and skew symmetric, those are neat special cases. But this is where it gets really mind-blowing. They're not just special cases, they are the literal DNA, the fundamental building blocks of every single square matrix out there.
And here it is, straight from the source. This theorem is a total game changer. It means that no matter how messy or random a square matrix looks on the surface, underneath it all, there's this beautiful hidden order. You can always break it down into these two pure components.
And check this out. Here's the secret formula that does all the magic. It's so elegant. You take your matrix A, you add its transpose, and cut it in half. That gives you the symmetric part. Then you take A, subtract its transpose, and cut that in half. And that's your skew symmetric part. Add those two pieces back together and you get your original matrix. Perfect.
Let's actually put this to the test with an example. So we grab some matrix, we'll call it B. We run it through the first part of the formula to get its symmetric sole, which we'll call P. Then we do the other half of the formula to get its skew symmetric part, Q. And you guessed it, when you add P plus Q, you get B right back. It's like taking apart a machine into its two core components and then putting it back together perfectly. It just works. Okay, so we've peeked inside the matrix. We've seen what it's made of. But what about what a matrix does? What about its power to change things? This leads us to one of the most powerful ideas in all of linear algebra, the ability to reverse what a matrix has done.
I mean, think about it. A matrix can stretch, shrink, rotate, and warp space. But what if you did all that and then wanted to go back? What if you wanted to hit Control-Z? Is there a big ol' undo button for matrices?
The answer is a huge yes. It's called the inverse. And here's the deal. For a matrix A, its inverse is another matrix that, when you multiply them together, totally cancels it out. You end up with this special matrix called the identity matrix, or I, which is basically the matrix version of the number 1. It puts everything back to exactly how it started. It's the ultimate reset button.
So obviously, the next big question is, how do we actually find this all-powerful undo button? Well, we don't just guess. There's a systematic process, a recipe, and it's built using just 3 simple tools called elementary row operations. These are the only 3 moves allowed in the game. That's it. You can swap any 2 rows, you can multiply a whole row by some number, as long as it's not 0, and you can add a multiple of one row to another. With just these 3 simple moves, we can unlock the inverse of a matrix.
All right, so here's the game plan. We start with this clever setup. A equals I times A. We put our matrix A on the left and the identity matrix I on the right. Then we start using our 3 row operations on the left side with the goal of turning A into the identity matrix. But here's the crucial trick. Every single move we make on the left, we do the exact same move to the matrix on the right. Okay, now watch what happens. As we apply our operations, you can see the matrix on the left slowly getting transformed into that clean identity matrix. But the real magic is happening on the right. That boring old identity matrix is being twisted and changed by those same operations, and it is literally building itself into the inverse. So by the time the left side becomes I, the matrix on the right is our answer. It's A inverse. So cool. Okay, so we've gone pretty deep into the math here. Symmetry, decomposition, inverses. It's cool stuff, but you might be wondering, why should I care? What's the point of all this? Well, it turns out this isn't just theory. This is the engine that powers a huge chunk of our modern world.
At the end of the day, being able to find the inverse of a matrix is how we solve really complex systems of equations. And that is everywhere. It's how engineers design bridges, how data scientists analyze massive data sets, how computer graphics engines render realistic images, and how cryptographers crack codes. This stuff is the foundation for physics, for economics, for basically everything that involves complex systems. It's incredibly important. So we figured out how to find this amazing undo button, but there's a twist. As one of the examples in our source material shows, sometimes you go through the whole process and you end up with a row of all zeros. The process just fails. The fact is, not every matrix has an inverse, and that leaves us with one last really fascinating question to think about. What does it mean when a system has no undo button? What happens when some actions can't be reversed?